In this video, I will show you how to solve a real-world problem that can be modeled by a system of equations using matrices. First, we need to define our variables so that we can set up the system of equations in the first place. In 7 years, Maria will be 4 times as old as Angelica will be then. The sum of their ages now is 71. How old will each of them be in 5 years? Now, normally I just look at what we are being asked to find and boom, that's what I use for my variables. How old will each of them be in 5 years? This problem is a little bit extra complicated because we are dealing it with 3 different time frames: 5 years, 7 years, and now. Instead of letting my variables represent how old they will be in 5 years, I think I will just let the variable represent how old they are now, and then just add 5 or 7 or whatever it will be. So let's let M equal Maria's age now. And let's let A represent Angelica's age now. Okay, let's see if we can get a couple of equations going. The sum of their ages now is 71. That's definitely going to be an equation right there. So I can know that M plus A is going to equal 71. That's the sum of their ages now. Now, in 7 years, Maria will be 4 times as old as Angelica will be then. So in 7 years, Maria will be, okay, so Maria's age in 7 years. That's Maria's age now plus 7. So this right here is Maria's age in 7 years. So in 7 years, Maria will be 4 times as old as Angelica is then. So Angelica's age in 7 years is Angelica's age now plus 7. So Maria's age in 7 years will be 4 times as much as Angelica's age in 7 years. So this is a valid equation. With a little bit of a distributive property, we will have M plus 7 is equal to 4A plus 28. Now I'm going to rearrange this a little bit to get the variables on one side and the constants on the other side. So for example, I will subtract 7 from both sides. So now I have M is equal to 4A plus 21. Now I will subtract 4A from both sides. So now I have M minus 4A is equal to 21. So I have this equation in standard form. Meanwhile, remember the first equation I have? M plus A equals 71. I think I'll bring that down now. So I have M plus A is equal to 71. Okay, so I've got these 2 equations. Let me highlight it for you. Boom. Alright, this is my system of equations that I'm now about to solve using matrices. In fact, I think I'll switch colors now. Okay, so it goes like this. I'm going to make myself a matrix equation starting with the coefficients. From the M and the minus 4, I'm going to have 1 minus 4. From the M and the A, the coefficients are 1 and 1. So here is my coefficient matrix. Now here comes my variable matrix, which is MA. And that is equal to the answer matrix, which is 21 and 71. Now I'm going to have to write a little bit smaller if this is all going to fit. Let's call this matrix C for coefficient matrix. Let's call this matrix V for variable matrix. And let's call this matrix A for the answer matrix. If I'm going to solve this matrix equation, I'm going to have to find C inverse. To find C inverse, I'm going to need the determinant of matrix C. So that's what I'm going to do first. What is the determinant of matrix C? That's the down diagonal minus the up diagonal. The down diagonal is 1 because 1 times 1. And I'm going to put plus. Now I said minus the up diagonal, but the up diagonal is negative 4. 1 times negative 4, that's negative 4. Minus a negative 4 is addition. So I'm going to have the fact that the determinant of matrix C is actually 5. Okay, now I can now do the inverse of matrix C, C inverse, in the following way. C inverse is going to be the reciprocal of the determinant, so 1 over 5 times the reverse negate matrix. Reverse negate. What do I mean? Well, looking at the down diagonal, you reverse these. Now they're both 1s, so you're not actually going to see anything, but I'm switching the numbers in this diagonal. If this were a 2 and a 3, the 3 would go here and the 2 would go here. They're both 1, so you can't tell. But now, negate. I'm talking about negating the up diagonal, which means that they don't move, but they change signs. So this 1 is going to become a negative 1, and this negative 4 will become a positive 4. Reverse negate. Now, C inverse then is what I'll get once I do this multiplication. Now I keep saying multiplication, but really multiplying by 1/5 is the same thing as dividing by 5. So I kind of think of it that way. So this will be 1/5, 4/5, negative 1/5, and 1/5. This is C inverse. Okay, great. Got it. Now that I have C inverse, I can solve this matrix equation. So looking at this giant matrix that I took up a lot of space with, what I have is the fact that matrix C times matrix V is equal to matrix A. If I were to multiply both sides by C inverse like this, C inverse on the left, another C inverse to the left. Together, these two make the identity matrix. So they basically cancel each other out because the identity matrix times a matrix doesn't change anything. So I basically now have the fact that matrix V is equal to C inverse times A. And I have those now. I have C inverse and I have A. So matrix V is going to equal C inverse, which is this 1/5, negative 1/5, 4/5, and 1/5. Alright, C inverse times matrix A, 21, 71. Alright, if I can multiply this out, I will have the answer. So that's what I'm about to do. I'm about to multiply this out. How do you multiply it out? That's a good question. You multiply each row times the column. So I'm going to take row 1, and even though it's a row, I'm going to actually write it vertically like this. So I've got 1/5 and 4/5 in this row. So I'm going to write 1/5 and 4/5. Even though it's a row, I write it vertically. Okay, now then I'm going to multiply by this column. And the column is 2171. Alright, so that's going to give me one thing. Alright, that's going to give me one element in my answer, the top element. Now I'm going to do that same thing with the bottom row. So the bottom row is negative 1/5 and positive 1/5. Okay, there's the bottom row. And again, I'm going to multiply it by the column, 2171. So if I multiply these together, let's see what I get. Well, that's going to give me 21/5 and 4 times 71. I need my 4 function calculator for this. 4 times 71 is 284. So I've got 200, and I'm going to add this. I've got 284 fifths. Alright, that's what I have in the top right now. Now in the bottom, I've got negative 21 fifths, and I've got 71 fifths. And I'm going to be adding those together. Okay, this is how I'm going to get my answer. Okay, let's keep going. Now, 21 plus 284. That's 305. So right there I have 305 fifths. Okay, is the top element of this matrix. And let's see, 71 minus 21 is going to be 50. So I'm going to have 50 fifths. Alright, now I'm closing in on the final answer for this matrix. 305 divided by 5, that's 61. Okay, so the top element here is 61. And then, of course, 50 divided by 5 is 10. Okay, so all this gives me matrix V, the variable matrix. Okay, and remember, the variable matrix was M and A, in that order, MA. So that means 61 is M. Okay, so that tells me that M is equal to 61 and A is equal to 10. In other words, Maria's age now is 61 and Angelica's age now is 10. So let's look back and see what we were actually supposed to find. Okay, so how old will each of them be in 5 years? So since we found their ages now, it will be easy to say how old they will be in 5 years. Okay, so since Maria is 61 now, she will be 66 in 5 years. Okay, and since Angelica is 10 now, she will be 15 in 5 years. And that is the final answer to the question. Let's do one more real-world problem. Red beads cost $1.30 per box. They are mixed with yellow beads that cost $2 a box. How many boxes of each color must be used to make 10 boxes of beads costing $1.72 per box? First, let's define our variables. I'd like to look at what we are being asked to find to help me define the variables. How many boxes of each color? So let's see, we have red and we have yellow. So let's let R be the number of boxes of red. Okay, of course we will let Y equal the number of boxes of yellow beads. Alright, there are two equations that we can write. One of the equations is going to be a money equation, and one of the equations will be a quantity equation. Let's start with the money equation. So, if R is the number of red boxes and they cost $1.30 per box, then the money equation is going to start out $1.30 for every red box. Okay, that's the amount of money spent on red boxes. And then it's $2 a box. You know what, I'm going to abbreviate this a little. I don't need the zero for this, so I'm just going to go ahead and put 1.3, but this is $1.30. And the yellow beads are $2 a box, so that's going to be $2 for every yellow box. Okay, so the amount of money spent on red boxes plus the amount of money spent on yellow boxes should equal the total amount of money spent. Now, they didn't give us that number as just a single number. We have to do a quick calculation. They told us that the mixed boxes are supposed to be $1.72 per box, and we know that there are 10 of them. So if I multiply 10 times 1.72, that's going to be a total of 17.2. Notice I'm just moving the decimal point one time over. Don't need a calculator or anything. So this should be the total amount of money spent on beads altogether. All right, the final cost per box times the number of boxes. Now the quantity equation is much more straightforward than that. There are 10 boxes. That's it. So that means number of red boxes plus the number of yellow boxes should add up to 10. So here we have a system of equations. Now I'm going to zoom in and use matrices to solve this system. So let's build our matrix equation starting with the coefficients of the variables. So I have 1.3 and I have 2, and then I have 1 and 1. So this is my coefficient matrix. Next comes my variable matrix, R and Y, in that order. Next comes my answer matrix, which is 17.2 and 10. Let's call this matrix C for coefficient matrix. This will be matrix V, the variable matrix, and this will be matrix A, the answer matrix. Now, to solve this matrix equation, I need the inverse of matrix C. To find the inverse of matrix C, I need the determinant of matrix C. So that's what I will find first, the determinant. Now that's down diagonal minus up diagonal. So down diagonal is 1.3. I'm multiplying. Up diagonal is 2. So I'm talking about 1.3 minus 2. So that means that the determinant of matrix C is going to be negative 0.7.
Yeah.
Okay, so 0.7 is also known as 7/10. So the determinant of matrix C is negative 7/10. That's important because the first thing we do when we find C inverse is we actually multiply by the reciprocal of this. So I'm going to do negative 10/7 times, and now I'm going to do reverse negate. Reverse negate. What do I mean when I say that? Why do I sound so crazy? I'm talking about reversing the down diagonal and negating the up diagonal. So the 1 and the 1.3 are going to switch places. So we'll have 1 and 1.3 like this. I will negate the up diagonal by changing the signs. They don't move, I just change the signs. So really this is C inverse right now. But I just need to go ahead and do this multiplication. Now I don't want to have decimals everywhere. I need exact values. So 1.3 is the same thing as 13/10. Okay, can you visualize that? If I did 13 divided by 10, that would give me 1.3. So I'm going to go ahead and replace 1.3 with 13/10, so I can make sure that I don't have any rounding going on. I want exact values. Alright, so 13/10. Okay, so I'm going to multiply everything by negative 10/7 and see what I get. So C inverse is going to be negative 10/7, positive 10/7, okay, positive 20/7, and okay, look, this one right here, when I multiply 10/7 times 13/10, okay, when I do this one times this one, I mean, yeah, it's negative. These 10s are going to cancel out. So that's going to give me negative 13/7. Okay, so that's what's about to happen. So negative 13/7. This is C inverse. Now that I have found C inverse, I can go ahead and solve this matrix equation. Okay, in fact, I think I'll just draw a line right here to separate out my work. So the matrix equation that I start off with is C times V is equal to A. Alright, C times V equals A. Now, if I multiply the left side of the equation by C inverse and the right side of the equation by C inverse, these will cancel each other out because the identity matrix. C inverse times C is the identity matrix. Alright, so this, all of this is really the identity matrix. And the identity matrix times another matrix does not change that matrix. Alright, so I'm just going to end up with matrix V is equal to C inverse A. So that's what I'm going to do right now. So matrix V should equal C inverse. Where are you, C inverse? There you are. Okay, matrix V will equal C inverse, which is negative 10/7, positive 10/7, 20/7, and negative 13/7 times A. And matrix A is 17.2. Okay, and again, I'm going to write this as a fraction. This would be 172/10. Okay, I feel like I should reduce that. Check it out. 17.2 is the same thing as 172 tenths, which reduces to 86 fifths. So when I do matrix A, normally I would put 17.2 and I'd put 10. But instead of putting 17.2, I'm going to go ahead and use the fraction 86 fifths. And look, if you went in your calculator and you did 86 divided by 5, 17.2. They're the same thing. Okay, so this is my 17.2 and 10. Okay, I just did this so I wouldn't have any rounding. I want everything to be exact, very precise. So when I multiply this out, I'm going to have my variable matrix. I will have the answer. So how do I multiply this? Well, when I multiply a 2 by 2 matrix times a 2 by 1 matrix, it's going to give me a 2 by 1 matrix. So I know I'm about to get a matrix that has 2 rows and 1 column. So look, I'm setting up a matrix that has 2 rows and 1 column right now. So how do I calculate it? I'm going to do the first row times the column, and that's how I'm going to get the first row of my answer. So I'll do the first row times this column and add the result. So I'm going to do negative 10 over 7 and 20 over 7. And then I'm going to multiply that times this column. So I'm going to multiply times 86 fifths and 10. And we'll see what we get from that. Now down below, to get the bottom row, I'm going to multiply the bottom row times this column. So I'm going to do 10 over 7 and negative 13 over 7. Okay, that's my bottom row. And again, times my 1 column. So this will be times 86 fifths and times 10. So this looks pretty ugly. I can't wait to see what's going to happen. Remember, whatever I get, I'm going to add these together. So let's see. If I multiply 10 times 86, actually let me cheat. 5 goes into 10 twice. So the 5 is gone. So I really am going to multiply negative 2 times 86. Okay, but everybody knows that 2 times 86 is 172. So I'm going to have negative 172 sevenths. Okay, and now I'm going to have 20 times 10. So that's going to be 200 sevenths. Okay, so that all of that is going to be, once I add those together, that'll be the top row. Now I'm going to do the same thing down here. And again, 5 goes into 10 twice. And again, 2 times 86 is 172, but this time it's positive. So I have 172 sevenths. And down here I have negative 130 sevenths. And look, I'm going to end up adding these together. So this is my top row and my bottom row. All I have to do is add these, and I'm home free. Okay, probably won't need that much space now. Okay, so 200 minus 172 is 28. So when I add these together, I'm going to get 28 sevenths in the top row. Now 172 minus 130 is 42. So that means adding these together, I'm going to have 42 sevenths. Okay, so my answer is taking form. I knew I would have a 2 by 1 matrix, and this is the top row and this is the bottom row. All I have to do now is reduce. Obviously 28 sevenths is 4 and 42 sevenths is 6. And that's it. This is matrix V, 4 and 6. So just remember that matrix V was R and Y, the number of red boxes and the number of yellow boxes. That means that R is equal to 4 and Y is equal to 6. Alright, so 4 red boxes and 6 yellow boxes. And that's it. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.